So in this example, solve the logarithmic equation, part A, log base 3 of x equals 3. I don't like that one because there's too many 3's. Let's make it 4. So, okay. So in part A, log base 3 of x equals 4. I claim you already know how to solve it. What would you do? By the way, is it obvious that why we call it a logarithmic equation? Because there's a log function in it, right? Yeah. So log base 3 of x equals 4. I heard the answer, you're going to just convert it to exponential form, right? What is this in exponential form? So really, you just need to know, to solve this equation, you just need to know how to convert from log form to exponential form. 3 to the 4 equals x. I wrote it as x equals 3 to the 4, right? I like having x on the left side. And what's 3 to the 4th power? 81. So 81 and done. There it is. Okay, notice what was happening here. We had a log function on one side and a regular old constant on the other, right? Whenever that happens, you're just going to switch to exponential form. It's going to be the same way every time. But what if you have like a log on both sides? I mean, technically, you could think of log base 4 of 5 as a constant because it's just a single output of a log function, right? But we'll think of it as a log function if you want, with a particular input. So how do you think things are going to change if you have the same log function on both sides, a single log on both sides? Yeah, you're going to drop the logarithm. It's based on this property up here, going from left to right this time. Notice what we did to solve exponential equations where we couldn't write both sides with the same base. It was like we were going from using this property from right to left. We took the log of both sides, right? Here, to solve this logarithmic equation where we have a single log on both sides, it's like we're using this property from left to right. Oh, if the log base a of x equals log base a of y, then you can say the inputs are equal, x equals y. So that's exactly what we're going to say here. We've got a single log on both sides. Just set the inputs equal. By that property, that has to be true. Now you have to make sure the bases of the logs are the same, base 4. As long as they are, and as long as you have a single logarithm on both sides and nothing else, so you can't have like a -5 out here, right? Forget it, it doesn't work. It has to be a single logarithm on both sides, okay? Then you can just drop the logarithm, set the inputs equal. And it's about as easy as you could expect, I suppose. X minus 3 equals 5, which means x equals 8. Now you do have to be careful on log equations, particularly to check your solutions. If you get a solution that creates the log of a negative number when you plug it back in, it's extraneous. It doesn't work, okay? Now x equals 8 is going to be fine, but just remember to check your answers. Remember, for any log function, you can't take the log of 0 or a negative number. That doesn't mean all negative numbers won't work for any logarithmic equation, because the inputs might be such that when you plug in a negative, you get a positive. But you've got to be careful, right? You've got to check your answers, and if you end up taking the log of a negative number, you got to throw that answer out. Part C, we have 6 times log of x equals -10. Okay, now notice we looked at 2 kind of prototypical cases. Either you have a single logarithm on one side and a regular constant on the other, or you can reduce it to a log on both sides. Which one do you think this is going to be? There's a 6 in front of it, but I see just one log function, don't you? I don't see a log function on the other side. So I think this is going to be more like part A. But first I better isolate the log x. How could I do that? Yeah, I mean, you could. Now, the complicated way of doing it would be applying the power rule. You don't want to do that. You could write this as log of x to the 6th, but then you make that input way more complicated. It's easier to realize this operation is multiplication, so let's just divide. Get it over to the other side. And we have log of x is equal, what's -10/6 reduced to? -5/3. When you don't see the base of the logarithm, what is it? So if you want, throw it in there, log base 10 of x. Okay, you have a single logarithm on one side, a constant on the other. What do? Exponential form. What would this look like in exponential form? Yep. Remember, the subscript in the logarithm is the base of the exponent. So if you convert this to exponential form, you get 10. The exponent is the guy by itself. 10 to the negative 5/3 equals x. I'm going to write it as x equals 10 to the negative 5/3. X on the left, in other words. Does that make sense to you? Well, I mean, that doesn't simplify very easily. You could write, what is the negative, just to remind you, what does the negative exponent mean? Yeah, so it's 1 over 10 to the positive 5/3. I'm just going to leave it there. You could play with that some more, but I'm just going to leave it like that. So kind of the general rule for routine log equations, there's two cases, Roman numeral 1. Reduce to a single logarithmic function on one side, convert to exponential form and solve. That was like part A. Or get a single logarithmic function on both sides, set the arguments, those are the inputs, arguments, inputs, same thing. Set the inputs or arguments equal and solve. That was like part B.